The galaxy is not what science fiction thinks it is. For more than a century, science fiction has imagined this same future. A single civilization spreads across the stars. Empires rise among the spiral arms. Galactic federations govern thousands of worlds. Trade routes connect distant systems. Armadas cross the galaxy as if it were an ocean. It is a powerful vision. But there is one problem. The universe does not allow it. Every fictional galactic empire, from classic space operas to modern science fiction, violates the same set of physical constraints. Not technological limitations that might be solved with better engines or smarter machines. Fundamental laws of physics. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. These stars are spread across a disk roughly 100,000 light-years in diameter. That number alone is difficult to comprehend. A single light-year is the distance light travels in 1 year, moving at nearly 300,000 kilometers per second. In that time, light covers about 9.46 trillion kilometers. Multiply that by 100,000. The result is a galaxy so vast that even light, the fastest thing in the universe, needs 100,000 years to cross from one side to the other. And light is not a spaceship. It carries no crew. It does not accelerate. It does not decelerate. It simply moves. Anything made of matter must travel slower. This is the first reason galactic empires are impossible. But it is only the beginning. The real structure of the Milky Way. Most people imagine the Milky Way as a flat spiral drawn on a classroom poster. A bright center. A few elegant spiral arms. A tidy disk of stars. That picture is useful for teaching introductory astronomy. But it hides the true complexity of our galaxy. The Milky Way is not a two-dimensional shape. It is an enormous three-dimensional structure, filled with billions of stars, clouds of gas, dark matter, stellar remnants, and gravitational chaos. The visible disk of the galaxy stretches roughly 100,000 light-years across. Near its outer edges, the disk is about 2,000 light-years thick. Closer to the center, the galaxy swells into a dense bulge reaching 10,000 to 12,000 light-years in thickness. But even that does not mark the boundary. Surrounding the visible galaxy is an enormous dark matter halo, extending more than 200,000 light-years in diameter. Ancient globular clusters orbit far beyond the bright spiral arms. Old stars drift through vast volumes of nearly empty space. The galaxy is not a flat map waiting to be crossed. It is a three-dimensional ocean of stars. And the stars themselves are astonishingly far apart. The distances between stars. In our region of the galaxy, known as the Orion Spur, the average distance between neighboring stars is about 4 to 5 light-years. That may not sound like much until you translate it into more familiar terms. 4 light-years is roughly 38 trillion kilometers. To understand how large that is, consider the most distant human-made object ever launched. The Voyager 1 spacecraft. Launched in 1977, Voyager 1 has been traveling through space for nearly 50 years. In all that time, it has traveled about 24 billion kilometers. That distance is enormous on a human scale. But compared to interstellar space, it is almost nothing. Voyager 1 has not even traveled 1% of a single light-year. At its current speed, it would take more than 70,000 years to reach the nearest star system, Alpha Centauri, which lies just 4.24 light-years away. And Alpha Centauri is the easiest possible destination. Every other star is farther. Many are hundreds, thousands, or tens of thousands of light-years away. The galaxy is not crowded. It is mostly empty. Between each point of light lies a void so vast that crossing it challenges everything we know about energy, engineering, and time. The 3 levels of interstellar expansion. When people talk about spreading across the galaxy, they often imagine a single process. Reach one star, then another, then another. Eventually, a civilization expands across the entire galaxy. But this assumption hides a critical mistake. There are actually 3 completely different activities that get confused with each other. Exploration, settlement, empire. Each one is vastly more difficult than the previous. Exploration. Exploration is the simplest form of interstellar activity. It means sending a probe, a signal, or a robotic spacecraft to another star system. The mission arrives, it collects data, it transmits information back home, and that is the end of it. Exploration does not require long-term survival at the destination. It does not require permanent infrastructure. It does not require transporting a population. Humanity already performs exploration within our own solar system. Spacecraft have visited Mars, Jupiter, Saturn, Pluto, and the outer boundaries of the heliosphere. Scaling this concept to nearby stars is extremely difficult, but not impossible. In fact, several real projects have already been proposed. Laser-propelled light sails could potentially send gram-scale probes to Alpha Centauri within a few decades. Exploration is hard, but it may be achievable. Settlement. Settlement is a completely different challenge. A settlement means establishing a self-sustaining civilization around another star. Not a probe, not a temporary mission. A permanent society capable of surviving independently. That means transporting or creating everything required for civilization. Food production, energy generation, medical systems, manufacturing infrastructure, education systems, scientific knowledge, governance structures, population stability. Every single one of these systems must operate without resupply from the home world, because the home world is light years away. If something breaks, the colonists cannot call for help. If a component fails, they must rebuild it themselves using local resources. Settlement is not a mission. It is the creation of an entire new civilization from scratch. Empire. Empire is something else entirely. Empire means coordination between many star systems, shared governance, shared economic systems, shared military power, shared culture. Information, people, and resources must move between systems quickly enough that the civilization can function as a single entity. This is what science fiction almost always depicts. Galactic federations, interstellar republics, imperial star empires controlling millions of worlds. But empire introduces a problem that exploration and settlement do not face: communication. For a civilization to act as one society, information must move between its parts faster than those parts change. And across the galaxy, that condition cannot be satisfied. The reason is simple. Information cannot travel faster than light. The first wall, the speed of light. The speed of light is not just a number. It is a fundamental property of space-time itself. Nothing carrying information, no particle, signal, or spacecraft, can exceed it. Light moves at 299,792 kilometers per second. At that speed, crossing the Milky Way still takes 100,000 years. A civilization on one side of the galaxy would wait 100 millennia to receive a message from the other side, and another 100 millennia for the reply. A single conversation would take 200,000 years. That is longer than most species exist. It is longer than recorded human history many times over. And that is the fastest communication physically possible. No technology can change it. No engine can break it. It is written into the structure of the universe itself. This is the first wall any galactic civilization encounters, the wall of distance and time. And beyond it lie even deeper barriers: energy, entropy, and the slow fragmentation of every network that tries to stretch across the stars. The speed of light trap. At first glance, the solution to interstellar travel seems simple: build faster ships, travel to nearby stars, establish colonies, repeat the process again and again until the entire Milky Way galaxy is filled with civilization. In theory, the process looks like a spreading wave. Each new colony sends ships outward to neighboring stars. Over time, the frontier expands. Eventually, the galaxy becomes populated with intelligent life. But this idea contains a hidden assumption. It assumes that faster ships can always solve the problem. Physics says otherwise. The barrier that stands in the way is not technological. It is fundamental: the speed of light. The ultimate speed limit. The laws of special relativity describe how motion works at extreme speeds. These equations were first developed by Albert Einstein in 1905. Over the past century, they have been tested repeatedly through experiments involving particle accelerators, satellites, and atomic clocks. Every test confirms the same conclusion. Nothing with mass can reach the speed of light. As an object accelerates closer and closer to light speed, its energy requirements increase dramatically. Eventually, reaching light speed would require infinite energy. Not enormous energy, not difficult energy, infinite. A spacecraft could approach the speed of light, but it could never reach it. This single rule defines the limits of interstellar travel, and once we apply it to the scale of the galaxy, the consequences become staggering. Crossing the galaxy. The Milky Way is about 100,000 light-years across. If a spacecraft could somehow travel at the speed of light itself, crossing the galaxy would take 100,000 years. But real spacecraft must travel slower, much slower. Let us examine several hypothetical scenarios. Scenario 1. 10% of the speed of light. A spacecraft traveling at 10% of light speed would move at about 30,000 kilometers per second. This is an astonishing velocity. For comparison, the fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches about 635,000 kilometers per hour during its closest approach to the Sun. 10% of light speed is about 108 million kilometers per hour. That is roughly 170 times faster than the fastest human-made object ever built. Even at this extraordinary speed, crossing the galaxy would take 1 million years. 1 million years ago, humans did not exist. Our ancestors were still primitive hominins wandering across prehistoric landscapes. Entire species have evolved and vanished within that time span. A single journey across the galaxy would last longer than the entire existence of modern humanity. Scenario 2. 1% of the speed of light. Now imagine a more conservative interstellar speed. 1% of light speed. That is still 3,000 kilometers per second, far beyond any propulsion system humanity currently possesses. At this speed, crossing the galaxy would take 10 million years. 10 million years ago, the evolutionary line leading to humans had not yet diverged from that of chimpanzees. The entire story of human civilization, from the first stone tools to modern spaceflight, fits comfortably inside this travel time. A single voyage, 10 million years. Scenario 3. 0.1% of the speed of light. Now consider a speed that might be achievable with advanced nuclear propulsion technologies, roughly 300 kilometers per second. At this velocity, a galactic crossing takes 100 million years. This is longer than the time that has passed since the extinction of the dinosaurs. Entire geological eras unfold within that duration. These timescales fundamentally change how we think about civilization. A mission lasting millions of years cannot rely on institutions, governments, or cultures that survive unchanged for such durations. Civilizations evolve, languages drift, societies transform. The longer the journey, the more disconnected the travelers become from the world that launched them. Time dilation and the illusion of faster travel. At extremely high velocities, relativity introduces an effect called time dilation. For objects moving close to light speed, time slows down relative to stationary observers. For example, a spacecraft traveling at 99.9% of the speed of light would experience time passing roughly 22 times slower than observers on Earth. For the crew aboard the ship, a journey that appears to take 100,000 years externally might feel like only a few thousand years internally. At first, this sounds like a solution, but it is not. Time dilation helps the travelers. It does nothing for the civilization they left behind. If the crew arrives at their destination after what feels like 4,000 years, 100,000 years have still passed on Earth. The civilization that launched them may no longer exist. Its language may be extinct. Its culture may be unrecognizable. The colonists arrive in a future where their origins are ancient history. Relativity does not preserve civilization. it fragments it. The energy catastrophe. Even if we accept the enormous travel times involved, another barrier quickly appears. Energy. Accelerating a spacecraft to relativistic speeds requires staggering amounts of energy. The kinetic energy required to move an object increases with the square of its velocity. Double the speed, you need 4 times the energy. At relativistic speeds, the situation becomes even more severe. The required energy rises dramatically as velocity approaches the speed of light. Let us examine a modest example. Imagine a spacecraft with a mass of 1,000 metric tons. That is roughly the mass of the International Space Station. Accelerating such a spacecraft to 10% of the speed of light requires approximately 4.5 times 10 to the 21st power joules of energy. For comparison, the total annual energy consumption of human civilization is roughly 5.8 times 10 to the 21st power joules. In other words, launching a single 1,000-ton interstellar spacecraft at 10% of light speed would require nearly the entire yearly energy output of Earth. And that calculation only includes acceleration. The spacecraft must also slow down at its destination, which doubles the energy cost. The tyranny of the rocket equation. The situation becomes even worse when fuel is considered. Most spacecraft carry propellant. To accelerate, they must throw mass backward at high speed. This relationship is governed by the rocket equation, a fundamental law of physics that describes how propulsion systems work. The rocket equation imposes a harsh constraint. The faster you want to go, the more fuel you must carry. But fuel itself has mass. And accelerating that fuel requires even more fuel. This creates a vicious cycle. For chemical rockets, achieving even a tiny fraction of light speed would require fuel masses larger than entire planets. Chemical propulsion simply cannot support interstellar travel. More advanced propulsion systems offer improvements, but they still face enormous challenges. Fusion propulsion. Nuclear-fusion drives are often proposed as a possible solution. Fusion reactions release far more energy than chemical reactions. In theory, fusion propulsion might achieve exhaust velocities of 3 to 5% of light speed. Even so, the numbers remain intimidating. To accelerate a 1,000-ton spacecraft to 10% of light speed using fusion propulsion would require tens of thousands of tons of fusion fuel. Mining, refining, and storing this fuel would require an industrial infrastructure spanning entire planetary systems. And all of that effort delivers only one spacecraft to one star system. Antimatter. Antimatter propulsion is even more energetic. When matter and antimatter collide, they annihilate each other completely, converting their mass into energy according to Einstein's famous equation, E equals mc squared. This reaction is the most efficient energy source known to physics. Unfortunately, antimatter does not exist naturally in usable quantities. It must be manufactured using particle accelerators, and the process is astonishingly inefficient. Producing a single gram of antimatter requires billions of times more energy than that gram could ever release. Antimatter propulsion does not solve the energy problem, it magnifies it. The cost of expansion. Now imagine scaling these missions. One ship to one star is difficult, but a civilization attempting space colonization on a galactic scale would need thousands of ships, then tens of thousands, then millions. Each ship requires enormous energy. Each mission consumes vast industrial resources. Each expansion wave targets more distant stars, increasing travel times and energy requirements. The cost of expansion does not remain constant, it rises. Eventually, the cost becomes unsustainable, and expansion slows, then stalls. But energy and propulsion are only part of the story. Even if a civilization solved the problems of travel and fuel, another barrier would emerge. A barrier that destroys every model of galactic civilization ever imagined. Communication. Because across the distances between stars, even information travels painfully slowly. And when communication breaks down, civilizations begin to fragment. The communication collapse. even if a civilization could solve propulsion, even if it could generate the enormous energy required for interstellar travel, even if it could send colony ships across the stars, another barrier would still remain: communication. Across interstellar distances, information travels at only one speed: the speed of light. And while that speed may seem incredibly fast, on the scale of the Milky Way galaxy, it becomes painfully slow. Slow enough to break every system that a civilization depends on. Messages that arrive too late. Consider the simplest possible case: two star systems separated by 4 light-years. This is roughly the distance between Earth and Alpha Centauri, the closest star system to our own. If a message is transmitted from Earth today, traveling at light speed, it will arrive at Alpha Centauri in just over 4 years. A reply sent immediately would return 4 years later. The total round-trip conversation would take 8 years. Even between the two closest star systems in the galaxy, a simple exchange of information spans nearly a decade. Now imagine a network of dozens of star systems spread across a region 50 light-years wide. A message from one side of that network to the other takes 50 years. A reply takes another 50 years. A single conversation now takes a century. The people who began the conversation may not live to see the response. Governments may change. Technologies may evolve. Societies may transform. The message arrives describing a world that no longer exists. The expansion of delay. As the distance between star systems increases, the delay grows rapidly. At 100 light-years, a round-trip communication takes 200 years. At 1,000 light-years, it takes 2,000 years. At 10,000 light-years, a round trip takes 20,000 years. And across the entire Milky Way, a simple conversation would require 200,000 years. That is nearly as long as modern humans have existed as a species. By the time a reply arrives, civilizations have risen and fallen. Languages have evolved beyond recognition. Entire cultures have vanished. Messages do not arrive as current information, they arrive as ancient history. Why coordination fails. For any civilization to function as a unified society, its different regions must coordinate with each other. Coordination requires current information. A government must know the current situation of its provinces. A supply chain must know current inventories. A military command must know the current location of its forces. Without up-to-date information, decisions become meaningless. Across interstellar distances, current information simply does not exist. Every message describes the past. A colony reporting a crisis 100 light-years away is describing events that occurred a century ago. By the time help arrives, or even a reply, the crisis has already resolved itself one way or another. The colony either solved the problem, or it collapsed. No response from the home system can arrive in time to matter. Coordination becomes impossible. The fragmentation of civilizations. As networks grow larger, communication delays begin to tear them apart. Imagine a civilization spanning 10 star systems within 20 light-years. Round-trip communication might take 40 years. That is difficult but perhaps manageable. Now expand the civilization to 100 star systems across 200 light-years. Round-trip communication takes 400 years. No government in human history has remained stable for 4 centuries. Policies change, institutions evolve, new technologies transform society. The colonies at opposite ends of this network no longer share the same civilization. They begin to diverge. Expand the network again to 1,000 star systems across 2,000 light-years. Round-trip communication now takes 4,000 years. At this scale, the civilizations at opposite ends are effectively strangers. They cannot coordinate economies. They cannot coordinate defense. They cannot maintain shared culture. They have become independent civilizations, not by choice, but by physics. The failure of interstellar economies. One of the most common ideas in science fiction is interstellar trade. Star systems exchange resources. Rare minerals move between planets. Advanced technologies spread through galactic markets. In reality, this kind of economy cannot function. Trade works when the cost of transporting goods is lower than the value of those goods. On Earth, shipping a container across the ocean costs a small fraction of the goods inside. But across interstellar distances, transportation costs become astronomical. Accelerating even a single ton of cargo to interstellar velocities requires enormous energy. The energy cost of transporting material between stars would exceed the value of that material by millions or billions of times. Even the rarest elements, gold, platinum, uranium, cannot justify that cost. There is nothing in the periodic table valuable enough to make interstellar trade economically rational. Every star system must rely on its own resources. Interstellar economies collapse before they begin. The drift of culture and language. Communication delays also cause cultures to drift apart. Human languages evolve quickly. After several centuries of separation, dialects become mutually unintelligible. After 1,000 years, the connection between languages can become difficult to recognize. Across interstellar distances, communication delays span thousands of years. Messages arriving from distant star systems would be written in languages that no longer exist. Even if the signal could be received, its meaning might be impossible to interpret. Technology would drift as well. Civilizations facing different environments and resources develop different solutions. One colony might specialize in biological engineering. Another might develop advanced robotics. Another might build entirely different forms of computing. Over centuries of independent development, their technologies would become incompatible. Shared standards would disappear. The collapse of a galactic network. As communication slows and cultures diverge, a large interstellar network cannot remain unified. Instead, it breaks apart into smaller regions. Each region consists of nearby star systems close enough to communicate within decades or centuries. Within these local clusters, cooperation may still be possible. But between clusters, the distances are too large. The delays are too long. The connections fade. The galaxy does not fill with one civilization. It fills with many small civilizations, each occupying a limited region of space, separated from one another by vast distances and immense spans of time. This fragmentation may explain one of the greatest mysteries in modern science, the Fermi paradox. If intelligent life can arise in the universe, and if the galaxy contains hundreds of billions of stars, why do we see no evidence of vast galactic civilizations? Perhaps the answer is simple. The laws of physics prevent them from forming. But communication and energy are still not the deepest barrier. Even isolated colonies face another enemy, one that operates everywhere in the universe, a force that slowly destroys every structure, every machine, every civilization. Entropy, the slow, relentless drift toward disorder. And in the end, entropy may be the ultimate reason why no civilization can spread across the entire galaxy. Entropy, the enemy of every civilization. Even if a civilization could overcome the enormous distances between stars, even if it could generate the unimaginable energy required for interstellar travel, even if communication delays fragmented its colonies into smaller regional clusters, there would still remain one final opponent. A force that affects every star, every planet, every machine ever built. Entropy, the second law of thermodynamics. The second law of thermodynamics is one of the most fundamental principles in physics. It states that in any closed system, the total amount of entropy, disorder, tends to increase over time. Energy spreads out, heat dissipates, ordered structures slowly fall apart. This process cannot be reversed globally. You can reduce entropy locally by using energy to maintain order, but doing so always increases entropy somewhere else. The universe always moves toward greater disorder. This law applies to everything: stars, planets, machines, and civilizations. The cost of maintaining order. Every structure ever built by an intelligent species requires continuous energy to survive. A building must be repaired, metal corrodes, materials fatigue, machines wear out, electronics degrade. Without constant maintenance, even the most advanced technology eventually fails. On Earth, civilization survives because it exists inside a massive support system, a planetary ecosystem, global supply chains, industrial infrastructure. If one system fails, another can replace it. If one region collapses, others can provide resources. But an interstellar colony does not have this safety net. A colony around another star is isolated. It must produce everything locally: food, energy, replacement parts, medical systems, manufacturing equipment, scientific instruments. Every piece of infrastructure must be maintained using only the resources available in that single star system. And the longer the colony survives, the harder that maintenance becomes. The slow decay of technology. Over long periods of time, technological systems begin to degrade. Machines break down. Factories wear out. Knowledge can be lost. Even with perfect planning, every civilization faces unexpected failures. Critical components fail faster than expected. Materials become scarce. Manufacturing processes drift. Small imperfections accumulate. Over centuries, the burden of maintenance grows. A civilization may begin with highly advanced technology, but maintaining that technology indefinitely requires a continuous stream of energy and resources. If that stream is interrupted, even temporarily, technological regression can begin. Human history provides examples of this process. The Roman Empire once built roads, aqueducts, and concrete structures that lasted thousands of years. But after the empire collapsed, many of those engineering techniques were lost. For centuries, Europeans could not reproduce Roman concrete. The knowledge had existed, but the industrial and institutional systems required to support it had disappeared. Now imagine this happening in an isolated interstellar colony. There are no neighboring civilizations to rediscover lost technologies, no trade partners, no external supply chains. If knowledge or infrastructure is lost, it must be reinvented from scratch, and that takes time. Sometimes centuries, sometimes longer. The uneven fate of colonies. Not every star system is equally suited for civilization. Some stars provide abundant energy.
Some planetary systems contain rich asteroid belts full of useful minerals.
Others are far poorer.
A colony orbiting a bright, stable star with plentiful resources may thrive for millions of years. But another colony orbiting a dim red dwarf star with limited materials may struggle from the beginning. Its energy supply may be weaker. Its planets may be tidally locked. Its environment may be harsh. Over time, these differences create an uneven landscape of survival. Some colonies flourish. Others slowly decline. Without assistance from neighboring systems, weaker colonies eventually collapse. Not dramatically, but quietly. Infrastructure fails. Population shrinks. Technology regresses. Eventually, the colony disappears. The lifetimes of stars. Even the stars themselves impose limits. Stars are not eternal. They are nuclear reactors slowly consuming their fuel. Our own sun will remain stable for roughly 5 billion more years before expanding into a red giant. Other stars burn faster. Massive stars live only tens of millions of years. Even relatively small stars eventually exhaust their hydrogen fuel. For any civilization that depends on stellar energy, the lifetime of its star defines the ultimate clock. Eventually, the environment changes. Habitability ends. The colony must either migrate or perish. A moving galaxy. While civilizations struggle to maintain their colonies, the galaxy itself is moving. The Milky Way galaxy rotates. Stars orbit the galactic center, completing a full revolution roughly every 230 million years. But this rotation is not uniform. Stars closer to the center move faster. Stars farther out move slower. Over millions of years, this differential rotation slowly rearranges the galaxy. Neighboring stars drift apart. Spiral arms shift. Entire regions of space change structure. Routes between colonies that once seemed stable may become inefficient or even impossible. The map of the galaxy slowly changes beneath any expanding civilization. The maintenance burden. Now imagine a civilization that has established hundreds or thousands of colonies across many star systems. Each colony requires continuous maintenance. Each colony requires energy. Each colony must constantly fight entropy. In addition, the civilization must maintain its interstellar infrastructure. Communication relays, navigation beacons, fuel depots, deep space monitoring stations. Each piece of infrastructure also degrades. Each one consumes resources. Each one must eventually be repaired or replaced. The larger the network becomes, the greater the maintenance burden. Eventually, maintaining the network costs more energy than the network itself provides. At that point, expansion stops making sense. Civilizations turn inward, focusing on survival rather than growth. The fragmentation horizon. All of these forces combine to create a natural boundary, a limit beyond which a civilization cannot expand while remaining coherent. This boundary can be called the fragmentation horizon. Inside this radius, star systems remain close enough to maintain communication and cooperation. Outside it, colonies become increasingly isolated. Eventually, they stop functioning as part of the original civilization. They become independent societies. Over time, each of those societies may create its own small cluster of nearby colonies, and those clusters may eventually fragment again. The galaxy does not become a unified empire. It becomes a patchwork of isolated civilizations, each one bounded by its own fragmentation horizon. And once we understand this, the silence of the galaxy begins to make sense. The universe may not be empty.
It may simply be too large for any civilization to remain connected. Thousands, or even millions, of intelligent societies may exist throughout the Milky Way, but each one occupies its own small island of stars, separated from the others by distances that no communication system can bridge. From our position in the Orion Spur, the galaxy appears silent, not because no one is there, but because the distances between civilizations are too great, the signals too weak, the time delays too long. But this realization leads to an even deeper question. If civilizations cannot form galaxy-wide empires, could they still slowly spread across the galaxy over millions of years? Could independent colonies reproduce the expansion process again and again? Could life eventually fill the Milky Way, not as one civilization, but as millions of isolated ones? The answer depends on the final constraint imposed by physics, the true scale of the galaxy itself, and why even the slow diffusion of civilizations faces limits far greater than we first imagine. The galaxy as an impossible frontier. At this point, a natural question appears. Even if civilizations cannot maintain a unified galactic empire, could they still spread slowly across the Milky Way galaxy? Not as a single coordinated society, but as independent colonies. Each colony founding new colonies. Each new world sending ships outward to the next generation of stars. A slow diffusion of civilization moving through the galaxy over millions of years. At first glance, this seems plausible. After all, the galaxy is extremely old. The Milky Way formed more than 13 billion years ago. Even if expansion moved extremely slowly, perhaps civilization would eventually reach every star system. This idea is sometimes called the interstellar diffusion model. Civilization spreads outward like biological spores. Each colony becomes the seed of further expansion. Over immense spans of time, the galaxy gradually fills with life. But once again, the numbers reveal a deeper problem. The true size of the galaxy. To understand the challenge, we must return to the scale of the Milky Way. The visible disk of our galaxy stretches roughly 100,000 light-years across. But the galaxy is not a flat surface. It is a vast, three-dimensional volume. If we approximate the galactic disk as a cylinder 100,000 light-years in diameter and about 2,000 light-years thick, the volume becomes enormous. Roughly 15 trillion cubic light-years. And this estimate ignores the massive halo surrounding the galaxy. Inside this immense volume lie hundreds of billions of stars. Each star separated by vast distances, each surrounded by planets, asteroids, and clouds of gas. Any civilization attempting to spread through this environment must solve a difficult logistical problem. Not simply reaching distant stars, but filling a three-dimensional space that grows dramatically as expansion continues. The cubic scaling problem. In three-dimensional space, expansion does not scale linearly. It scales with the cube of distance. If a civilization doubles the radius of its territory, the volume it must occupy increases 8 times. Triple the radius, and the volume becomes 27 times larger. Increase the radius by a factor of 10, and the volume expands 1,000 times. This means that every step of expansion becomes harder than the previous one. The farther a civilization spreads, the more territory it must maintain. More stars, more colonies, more infrastructure, more communication pathways, more energy consumption. The cost of expansion grows faster than the territory itself. Eventually, the system becomes impossible to maintain. The geography of the Milky Way. The galaxy is also far from uniform.
Some regions contain dense clusters of stars, others are almost empty. The spiral arms of the Milky Way contain most of the galaxy's stars. Between these arms lie enormous inter-arm voids where stellar density drops dramatically. A civilization expanding along a spiral arm may encounter many nearby stars, but attempting to cross between arms could require journeys of thousands of light-years through sparse regions of space. The galaxy resembles a landscape filled with mountains, valleys, and deserts. Some paths are relatively easy, others are nearly impassable. Every expansion route faces unique obstacles. Radiation environments near the galactic center become extremely intense. Gravitational interactions between nearby stars may destabilize planetary systems. Outer regions of the galaxy may lack sufficient resources to support long-term colonies. The Milky Way is not a uniform frontier waiting to be settled. It is an uneven and constantly changing environment. Time changes the map. Another complication emerges when we consider time. Stars are not stationary. They orbit the center of the galaxy at enormous speeds. Our own sun travels through the galaxy at roughly 220 kilometers per second. A full orbit around the galactic center takes about 230 million years. Over millions of years, stars drift into entirely new positions. A star system that was once close may become distant. Regions of high density may disperse. Entire stellar neighborhoods rearrange themselves. For civilizations expanding over tens of millions of years, the map of the galaxy slowly changes beneath them. Navigation becomes increasingly difficult. Routes that once existed disappear. New routes emerge unpredictably. Expansion must constantly adapt to a moving target. The limits of diffusion. Even if civilization spreads slowly across the galaxy, diffusion eventually encounters limits. Each colony must invest enormous resources to launch its own interstellar missions. Each mission requires energy, materials, and time. Colonies facing difficult environments may never achieve the technological level required for interstellar travel. Others may collapse before expansion becomes possible. Some colonies may simply choose not to expand. Over millions of years, the expansion wave becomes uneven. Certain regions fill with colonies. Other regions remain empty. Eventually, the process slows, not because it is impossible to expand further, but because the cost of doing so becomes too high. The frontier stops advancing. The silent galaxy. This perspective offers a powerful explanation for the Fermi paradox. The paradox asks a simple question. If intelligent life is possible, and if the galaxy contains hundreds of billions of stars, why do we see no evidence of galactic civilizations? Why do we observe no megastructures, no galaxy-spanning empires, no signals from advanced alien societies? The answer may not be that life is rare. It may be that civilizations remain localized. Each one spreads only as far as physics allows. Each one forms a small cluster of nearby star systems. Beyond that cluster, expansion becomes too slow, too expensive, or too unstable. From a distance, the galaxy still appears empty. Islands of civilization. Instead of a single galactic empire, the Milky Way may contain countless independent clusters of civilization. Each cluster might span a few dozen stars, perhaps a few hundred. In rare cases, maybe a few thousand. Within those clusters, communication and cooperation remain possible. Civilizations may build extraordinary technologies, orbital habitats, artificial worlds, massive space-based industries. But beyond their local region, the distances become too great, the delays too long, the costs too high. Each cluster becomes an island of intelligence, separated from others by vast oceans of space. The galaxy as an archipelago. Seen from this perspective, the Milky Way resembles a cosmic archipelago, a scattered collection of islands across an enormous ocean. Each island represents a cluster of civilizations occupying a small region of the galaxy. Between them lie thousands of light-years of darkness. Signals may travel between these islands, but they take so long to arrive that meaningful communication becomes impossible. To us, the galaxy appears silent, but silence does not necessarily mean emptiness. It may simply mean distance, and this realization changes the way we think about our place in the universe. Humanity may never build a galactic empire, but that does not mean our future among the stars is impossible. It simply means our civilization will always remain local, bound to a small region of the galaxy. A tiny island of light in an ocean of cosmic darkness. But there is one final perspective left to explore. If the universe prevents civilizations from conquering entire galaxies, what kind of future does it actually allow? What does a realistic cosmic civilization look like? And what might humanity become if we learn to live within the limits of physics rather than trying to overcome them? The universe favors isolation. For centuries, humanity has imagined the same cosmic future. A civilization expanding endlessly across the stars. Galactic federations governing millions of worlds. Interstellar trade networks connecting distant systems. An empire stretching from one side of the Milky Way galaxy to the other. It is a vision of boundless expansion. But the deeper we examine the laws of physics, the more that vision begins to change. The universe does not forbid intelligence. It does not prevent civilizations from reaching the stars, but it quietly imposes limits on how far that expansion can go. Limits written into the fabric of space-time itself. The hard boundaries of physics. Every barrier we have examined points toward the same conclusion. The speed of light limits how fast information can travel. Relativity ensures that no spacecraft can exceed that limit. The enormous distances between stars stretch communication across decades, centuries, or millennia. Energy requirements for interstellar travel grow to staggering levels. The farther a civilization expands, the more energy it must invest simply to maintain its infrastructure. Meanwhile, entropy works constantly in the background. Every machine wears down, every structure degrades. Every colony must continuously fight against disorder just to survive. These forces combine to impose a natural boundary. A maximum radius within which a civilization can remain connected. Beyond that radius, colonies drift apart. Not physically, but socially, culturally, technologically. They become independent civilizations. A galaxy of independent civilizations. If intelligent life arises in many places throughout the galaxy, then the Milky Way may not be empty at all. Instead, it may contain thousands or millions of small civilizational clusters. Each cluster occupying its own region of space. Each one expanding only as far as communication delays and energy limits allow. Within those regions, civilizations may accomplish extraordinary things. They may build habitats around entire stars. They may terraform worlds. They may develop technologies far beyond anything humanity can currently imagine. But they remain local. Their influence extends only across a few dozen or perhaps a few hundred nearby star systems. Beyond that distance, the universe grows too large. Signals take too long, expansion becomes too expensive. And the cluster fragments. Why the galaxy appears silent. From our position inside the Orion Spur, the galaxy appears strangely quiet. We have searched for radio signals. We have scanned nearby stars for signs of technology. We have listened for whispers from distant civilizations. So far, we have heard nothing. This silence has puzzled scientists for decades. It lies at the heart of the Fermi paradox. If intelligent life is possible, and if the galaxy is so vast, then where is everyone? Perhaps the answer is not that civilizations are rare. Perhaps it is that the universe prevents them from becoming visible across great distances. Civilizations may exist, but they are isolated. Separated by tens of thousands of light-years of empty space, their signals fading into cosmic noise long before they reach us. The galaxy is not empty. It is simply too large for its inhabitants to hear each other. Humanity's place in the galaxy. This perspective does not make the future smaller. In many ways, it makes it more profound. Humanity may never control the entire Milky Way galaxy, but that was never necessary. Even a tiny region of the galaxy contains extraordinary possibilities. Within just 100 light-years of Earth, there are thousands of stars. Many of those stars likely possess planets. Some may contain environments suitable for life. If humanity learns to travel between these nearby systems, our civilization could expand across an entire stellar neighborhood. A cluster of worlds, each one different, each one a new frontier. Within that cluster, communication would still be possible. Cooperation could still exist. Civilization could flourish across multiple stars, not as an empire, but as a community. The archipelago of intelligence. Perhaps the future of the galaxy is not a single empire. Perhaps it is something more beautiful. Imagine the Milky Way as a vast ocean. Across that ocean lie countless islands. Each island is a cluster of star systems, each one home to its own civilization. Each one developing its own culture, its own science, its own understanding of the universe. Some islands may never know the others exist. Some may exchange faint signals across the darkness, but none will ever rule them all. The galaxy becomes an archipelago of intelligence, a scattered network of civilizations, each one lighting its own corner of the cosmic night. A fire in the darkness. And here, in a small spiral arm of an ordinary galaxy, humanity is just beginning its journey. We have not yet reached another star. Our spacecraft have barely crossed the boundary of our own solar system. But we have begun to understand the structure of the universe that surrounds us. We are learning its rules, its limits, its possibilities. The galaxy may never belong to us, but perhaps that was never the goal. Perhaps the purpose of intelligence in the universe is not conquest. Perhaps it is understanding. Each civilization, in its own small region of space, asking the same questions. Looking out into the darkness, building instruments to study distant stars, trying to understand the cosmic story that produced them. The quiet universe. The Milky Way may never echo with the voices of a single galactic empire. Instead, it may remain a vast and quiet place, filled with countless civilizations separated by unimaginable distances, each one living within its own small island of stars, each one burning its own brief light against the darkness. And somewhere, perhaps far beyond our reach, other minds may be doing exactly what we are doing now, looking up at their night sky, wondering if they are alone, listening, waiting, and slowly discovering that the universe is not empty. It is simply vast. And within that vastness, every civilization becomes its own island of light.